Hello AP Physics 1, it's Mr. Ng, and here's Giancoli Chapter 7, Number 9. I chose this one because there's a lot of converting that you need to do. It's a really kind of a funky problem. So here, this problem is talking about how there was a bunch of crazy winds during the Chicago storm, and it wants to know how strong that wind is, right? Supposing you're standing here, right, dealing with the wind. So let's go through this problem and figure out what units we got to deal with. So during the Chicago storm, winds can whip horizontally at speeds of 100 kilometers an hour. V is 100 kilometers an hour. This is gonna suck because it's not in meters per second, so we got to do a little bit of converting here. If the air strikes a person at a rate of 40 kilograms per square meter, which sucks, right? Because 40 kilograms per square meter, meters squared, that's not the person, that's like this generic space. So we'll need to do some converting here. It's brought to rest. Estimate the force of the wind. Assume the person is, here we go, 1.5 meters by 50 meters. Okay, so the unit for the flow of the wind is 40 kilograms per meter squared, but one person is actually 1.5 meters times 0.5 meters. That's going to be 0.75 meters squared. Okay, so a little bit of conversions. Number one, let's convert the flow from 40 kilograms. You know what? I'm going to start with the person. If you have a 0.75 meter squared person, and we know that for every 1 meter squared, you get 40 kilograms of air, of wind. That means there's 30 kilograms of wind for this person. All right, 30 kilograms per second. Right, so here we get to change this. Let's not use this number. We're talking about 30 kilograms of wind for this person. That's the first bit of conversion that we got to do. Right, let's circle that. And then here, 100 kilometers an hour. I hate it when they do that. So we got to convert that to meters per second, right? So kilometers an hour. We know that every 1 kilometer is 1,000 meters. We know that every 1 hour is 60 minutes. And then we know that for every 1 minute, it's 60 seconds. So if you do that math correctly, you'll get 27.77 meters per second. Okay, so now we got kind of the numbers that we can fill in with our impulse equation. Just a reminder, impulse is equal to force times the change in time, or if you want to change it around, force is equal to impulse divided by time, or force is equal to mass times the change in velocity, meaning velocity final minus velocity initial over the change in time. All right, so let's figure out our variables. We got our mass, we need our velocities, and we need our time, n dvt. Our m is going to be 30 kilograms of wind. The final velocity, let's do final and initial, right? Our final velocity is 27.77 meters per second. Our initial, we assume that wind just starts from nothing, and all of these was over an increment of 1 second. So force is equal to 30 times 27.77 divided by 1 second. So our force is going to equal to 833 newtons. The sig figs are all off. If I look at it, it looks to be maybe 2 sig figs. Actually, the lowest one is actually 1 sig fig. So really the force is just 800 newtons. Okay, that's part one, done. Part two, compared to the typical maximum force of friction with a friction coefficient of 1. Okay, so let's see, the force of friction, if you don't remember, is the friction coefficient times the normal force, which is going to be the friction coefficient times mg, basically, right? So it's going to be 1 force of friction is going to be 1 times a typical person has a mass of 70 kilograms, and then g is 9.8. If we do that math, that's 686 newtons. Okay, so the force of the wind is way bigger than the normal force on a person. That means during the Chicago storm, people get whipped up and fly away. There you go. Thank you, physics.